For our afternoon keynote, I am very pleased to introduce Shawn Riley. Shawn Riley is the Chief Data Officer at DarkLight Cybersecurity Company, which is also what we were talking about before. I'm glad they also have a Chief Data Officer. Following his 8 months as a Senior Advisor to the company, he does a lot of work with their product strategy, vision, and driving AI adoption within the company. Please.
Can everybody hear me okay? Okay, great. So I'm Shawn Riley. I'm a cybersecurity scientist as opposed to a data scientist. So I've actually started into cybersecurity back in the early 90s and have been progressively working on more and more complex cybersecurity problems. For the last 8 years or so, I've been really focused in on symbolic AI or knowledge engineering. And that primarily comes from spending a lot of time with a lot of humans, teaching them how to do different things and wanting to capture that human experience, that tradecraft in artificial intelligence so that way the AI could apply it and produce scientific arguments on behalf of the investigators. So I normally start off with a simple slide of explaining that science isn't anything to be scared of, that it's mainly us investigating evidence over time so we can make sense of it and explain it, and then it's critiqued over time, those explanations, and our knowledge improves and we move forward. I want to include the formal definition of cybersecurity science. The top paragraph is from the NSA's Science of Security organization, and that's really thinking not only operational security science, but research security science. So it's thinking about the whole field and building that body of knowledge about what we know, right? The bottom paragraph here is from the 2011 Three Nations Joint Statement of Understanding on Cybersecurity Science. And it's the three nations are Canada, the United Kingdom, and the United States. And they really identified that there's 7 core themes that are strongly interrelated. Common language, core principles, attack analysis, measurable security, risk, agility, and human factors. So when you think about security operations, or when you go in and have security within an enterprise, half the roles are security engineering, or more than half the roles are security engineering. So that's all your architects, developers, engineers. They're really focused on building and maintaining and configuring the enterprise. Then you have all the security science roles. So everything from a risk analyst who's investigating the vulnerabilities and weaknesses in an organization, incident response investigators, insider threat investigators, threat intel analysts are all cybersecurity science roles. So I tend to focus on operational cyber defense knowledge because that's where I've spent pretty much the last 30 years. And when I think about operational cyber defense knowledge, what is it? Well, it's really built on kind of a foundation where we think about information security kind of providing our cyber hygiene, right? That's really about identifying all the people, devices, configurations, who's a privileged user, what their permissions are, all of that kind of information. And then on the other side, we really want to understand what's the impact of all those people and devices and applications and services. What parts of the business or the mission do they support? Because if a person or a device or a service goes down, I want to know what the business or mission impact is. And then down here at the very bottom, you see the cyber resiliency techniques in engineering. So that's all our cyber defenses, everything from continuous diagnostics and mitigations to architectural diversity, right? It's all the different things that we do to protect and detect and respond and recover. And where does that kind of knowledge come from? Where do we focus on the cybersecurity science side of validating or getting knowledge? Well, we spend a lot of time applying data science to the data sets, right? And a lot of the data science that we apply in cybersecurity science applies inductive inference, right? To make predictions based on the patterns in the data that we're looking at. And that's really aligned, obviously, to the data level. When I think about information sharing, it comes over communications, right? So we generally get a lot of threat intelligence shared with us. We get the National Vulnerability Database sharing vulnerability information with us. We get a lot of information from different sources that are communicated to us, where we're not the source of that knowledge, right? And finally, the area that I've been focused in a lot is applying deductive inference. And really that's about the knowledge engineering, I guess, behind that is really about the integration of information, context, experience into knowledge, right? So when I think about activities like integrated cyber, so if you're familiar with NSA and DHS are sponsoring a framework called Integrated Adaptive Cyber Defense out at Johns Hopkins University. And it's really about integrating cyber, right? And so they started off with integrating technologies, and that's a lot of API integrations and making sure that you can access APIs to orchestrate different actions. But it's also about integrating cyber defense information and threat information and all this kind of knowledge that I have, all this different sources of information and the context to understand those, and the experience in applying that information to solve problems into integrated knowledge. And so when I think about integrated knowledge, it makes me think about the 4 primary types of knowledge models that we use in cyber defense. And so if you think about the very bottom, easiest to build, easiest to use knowledge model is a dictionary. Just above the dictionary is a taxonomy. Above a taxonomy is a thesaurus. And above a thesaurus is a conceptual model or an ontology, right? So when you think about things like STIX2, for example, STIX being the Structured Threat Information Expression, it's a JSON language with a JSON schema for the knowledge model, which means that it's going to be right down here, right close to where XML schema is. When we think about another language that's being developed in the community called the Cyber Investigation Analysis Standard Expression, that is actually being developed as an RDF schema and a conceptual model because they want to support semantic interoperability. Now, the cool thing about these knowledge models is each one going up can be used in place of the ones below it. So in other words, an ontology can be used in thesaurus mode, or taxonomy mode, or dictionary mode. It doesn't necessarily have to be a full-blown ontology used every time. But if you're going to be developing data models, I've seen a lot of organizations go through, do this whole transformation, and only focus on lower-level knowledge models. So to kind of apply this operationally, I thought it would be fun to look at how cybersecurity scientists look at the cyber OODA loop. And so the Integrated Adaptive Cyber Defense framework that I mentioned earlier, that's sponsored by NSA and DHS, is really this construct over here. And the traditional OODA loop, developed back in World War II for combat air-to-air fighting, is over here on this side. And really, it's about sensing. And all of our sensors are out there doing structured observations, right? About making sense of those observations that they're seeing. It's about making a decision based on making sense of what we're seeing and then taking some kind of action, right? So when I think about sensing, right, as I said, that's kind of the equivalent, the cyber equivalent of our senses, right? We generally use our senses in science, what we can see, smell, hear, taste, right? In cyber, it's where we can place our different sensors, right? So when I think about deploying sensors in the cyber ecosystem or the cyber environment, I generally have to think about the different layers within the cyber environment, and we generally consider those layers a terrain. And so if you think about this construct, it might be a busy slide, but if I look at layer 0 down here, it's a geographic layer. So if I think about any of these physical devices or a person or an organization, they're physically located somewhere. So I wanted a geographic layer down at the bottom. And then layers 1 through 7 is the traditional OSI model. Those who work on networks, understand what the OSI model is, you often hear cybersecurity vendors say, oh, I'm a layer 2 solution. This is what they're talking about. They're down here at this data link layer. Above the network layers, we put a machine language layer. So if you think about like a BIOS on your motherboard in your computer, we know for a fact that there's lots of viruses that target that. So that's a layer in itself. And you think about embedded systems and the Internet of Things, they might not have a full-blown operating system. They might just have some kind of embedded code on a chip somewhere. Above the machine language is the operating system, then software applications, and then persona being anything that ties the humans back into the cyberspace. And so when we think about cyberspace, it's really this layer 11 through 2, and it's wedged between two physical objects, the physical device and the physical person up here at layer 12. And that person always belongs to an organization or normally belongs to an organization, and they're normally in some place that's responsible to a government. And also as a defender, I'm also getting information such as threat intelligence or vulnerability information from the government. So I want to be able to attribute that's where I'm getting that data from. When I look at those same layers as a cybersecurity scientist or as a CISO defending my network or my customers' networks, I often have to think about those layers of the cyber terrain in the context of the defenders and the attackers, right? We have to understand what the attacker's use of technology is, what the attacker's TTPs are, and where they're at in different layers, because that's going to tell us what sensors or solutions can actually see those, or where I might have gaps. And being able to map the defender's solutions and mitigations to those same layers to have an understanding that if an adversary is doing something, do I even have a response? So that brings us into sense making. When I think about down at the data level, and it used to be, back when I first started, that humans were supposed to dig through all this data. We just didn't have enough time to do it, and half the systems were not even set up to audit the things that they were supposed to audit. And a lot of the system administrators back in the 90s would set up their audit logs to delete at the end of the day, so that way it didn't fill up their disk, right? Because disks weren't very big back then. But over time, we realized, hey, there's a problem. We're not looking at all these different data sets that we have, and so we've been applying data science and before that statistical algorithms and analysis to these data sets for a long time. Ever since I joined the military back in the early 90s and started working on cybersecurity, there's always been some kind of statistical analysis on different data sets. I remember spam being a big focus of machine learning back in the 90s to identify spam. The knowledge engineering expert systems, the symbolic AI, they're a little bit more like Sherlock Holmes, deducing facts based on the facts that are present in the evidence. And so I often use this graphic to help people better understand the machine learning side, where it's down here and it's focused on the data and it's making observations, looking for patterns, and then giving us a tentative hypothesis. And on the knowledge engineering side, we can actually have cognitive playbooks that say, hey, let me grab that tentative hypothesis, run this through a human cognitive process, and validate it to identify any fallacies or cognitive bias, and confirm or identify the fallacy of that tentative hypothesis, right? And then I want to make sure that I can take that information and start deducing facts into it from community knowledge or enterprise knowledge or the analyst's own knowledge. And so when I think about examples of that, so cybersecurity is filled with tons of frameworks and languages. If you've never heard of the cybersecurity measurement and management architecture, it's about 30 to 45 different common standardized languages for everything from threats to vulnerabilities to weaknesses to attack patterns. It's really worth looking at. This particular graphic up here is the OODA cyber threat framework. If you read the OMB circular that came out earlier this year, all the federal agencies were directed to implement and use a cyber threat framework for the consistent categorization and characterization of threat events, because they said federal agencies really suck at being able to consistently identify and characterize the threats in their environment. So they wanted everybody to move to a common framework, and that's this OODA framework. And so it really has 4 stages of a cyber attack lifecycle. They said that, everybody and their uncle was coming up with their own kill chains. Lockheed Martin started off by copywriting their kill chain, their 7-stage kill chain. So everybody else kind of started making their own kill chains because they couldn't use that one. So the OODA said, hey, we're going to create a simple 4-stage cyber attack lifecycle that we can map all those other proprietary kill chains into. And so it really starts off with preparation, engagement, and then it goes boom. This is where they get into your enterprise right here in the middle. They establish presence inside your enterprise, and they have some kind of effect or consequence. And then it gets down to these objectives of the adversaries. But the problem is most of the commercial community, and even a lot of the defense community, doesn't use the OODA cyber threat framework for objectives or tactics or activities, actions. They're using MITRE's pre-attack and attack for those tactics and techniques. So as a cybersecurity scientist and a knowledge engineer, I have to understand, how do I integrate this OODA cyber threat framework knowledge with MITRE's pre-attack and attack? And oh, by the way, I also have threat intelligence in the form of sticks that's also coming in and speaking a different language than attack or the OODA cyber threat framework. So now I have to integrate all these sources of threats so I can even just make sense in a consistent manner of this community cybersecurity knowledge, right? And that brings us into decision making. So when I think about decision making, a guy named Keith Willett up at NSA, he's the lead architect for active cyber defense up there, or at least he was last time I checked, published a paper about cybersecurity decision patterns. And he basically said, he's really focused on knowledge engineering to support active cyber defense and capturing that human analyst process. And cybersecurity decision patterns are really the codification of a problem, the context surrounding that problem, and what the solution to that problem is. So that solution is, if the problem is a threat, the context surrounding that threat, then I'm going to have some kind of response or mitigation or some kind of course of action that I'm going to do in order to provide the solution to that. When I get into thinking about the solution as a defender that I want to have on the adversary's activity, the problem that I'm seeing, I also now have to think about NIST 800-160 Volume 2, the Cyber Resiliency Engineering Framework, and resiliency effects. So if I want to redirect the adversary, there's kind of 3 types of effects that I could have in support of redirecting that adversary. I can deceive them, I can divert them, and I can deter them. And really, these 3 up here are a little bit different than the rest of the effects because these indicate that there's a human on the other side. These rest of these could be applied to natural disasters like fire or earthquake or flood, if you wanted to, right? So, but these ones up here are more specific because you can't deceive a fire, right, or an earthquake. But if you think about all these different effects, if you're responding to a threat, ultimately you want to make sure that you can expunge the adversary out of your network. You want to make sure that you can recover your system or your mission, right? You want to make sure that you can do things like reveal what you know about the adversary to people that you're sharing information with through sharing threat intelligence. And so when I think about trying to combine the ability to identify the threat and then identify what effect can I have on that threat, it brings me to what I like to call the cyber effects matrix, where along this side, over here, you have that OODA cyber threat framework. You have preparation, engagement, presence, effect, and consequence. Underneath each one of those stages of the cyber attack lifecycle that the adversary is going through are the objectives that they have at that time. So these are all about planning and preparation. These are all about setting up their infrastructure, compromising third-party sites. This is where the boom happens. This next phase is them being inside and establishing activity within your network and moving around. And this final stage is all about the threats where they're having some kind of effect or consequence. Along the top, what you see is those NIST 800-160 Volume 2 Cyber Resiliency Effects. And then what we want to do is be able to look at the objectives of the adversary and what effect I can have on those. But remember that underneath these 26 objectives are close to 400 behaviors that are commonly known, because remember, these come from MITRE's adversary tactics, techniques, and common knowledge. So these are close to 400 behaviors or activities that the adversaries are going to do as they move down that cyber attack life cycle. And underneath those 400 different techniques or activities are thousands of procedures or individual recipes. So if you imagine that an activity is baking a chocolate cake, the procedures under there might be all the different recipes that people have for baking chocolate cakes, right? And it's our ability, we have to have the knowledge of those recipes to be able to identify not only the recipe, but potentially who the recipe belongs to as part of our investigation, right? Because we want to understand what groups are attacking us. If I'm getting the same group attacking me again and again and again, I want to build more defenses against that group, right? That brings us down to acting. So acting is where we've invested a lot of time over the last 4 years or so on security automation and orchestration. When you think about security automation and orchestration, you generally think about the playbooks they build there. Those are different than cognitive playbooks that we use in knowledge engineering. They're mainly action or mechanistic action playbooks, which basically means it's a Python script or a PowerShell script that's executing some kind of action or response action, like re-image that device, or take this piece of malware and run it over to the sandbox and execute it. So in common languages, even within orchestration, the common language for command and control is OpenC2, right? So you want to make sure that if you're, like, I build an expert system that's making sense and making decisions about what action to take, so my expert system has to be able to communicate in a standardized language to orchestrators, hey, I need you to take the following actions and report back to me what your status is. And that's really what this framework for IACD is really about. It's about integrated adaptive cyber defense and integrating the kind of technology integration initially, all these different types of technologies together. And all the technology you see on there have already gone through integration within this framework. So, and that kind of brings us to the feedback stage of the cyber OODA loop. Because we've done all these things, we did sensing, sense-making, decision-making, and acting. And at each stage, there's an opportunity for feedback for improvement. So if we think about the feedback in the sensing area, do we even have the ability to see all those 400 different activities that I listed from the combined pre-attack and attack tactics and techniques that the adversary are going to do? How many of those do I actually see? Do I actually have a sensor? Because if I don't have a sensor that can see it, then I have no data, right? If I have no data, I have nothing to analyze. I'm not going to see the adversary in those areas. When it comes to the non-symbolic AI making predictions, we want to make sure that we can provide the feedback to that analytic solution on fallacies or cognitive bias that were uncovered during the expert systems cognitive playbooks that are used to validate those predictions coming from different data sets and sensors. When we come to the cognitive playbooks that are used in the symbolic AI side to capture the human experience in applying that knowledge, we generally use peer review because we can take those cognitive playbooks that are 100% transparent and explainable because they're based on human knowledge, and import and export those along with the knowledge models, the ontologies that go with those, and what's called the reify configurations or the mappings between the raw data set and those knowledge models. Those can all be exported for peer review, either internally or externally. So if you think about somebody like, I don't know, you might have DISA build a whole bunch of cognitive playbooks for doing different validations of threats, and you might say, oh, they might exchange those with Cyber Command, who does validation, right, to validate the tradecraft in those knowledge models, or vice versa. We really want that ability for transparency and explainability and the ability to produce scientific arguments with those cognitive playbooks. So we want to make sure that peer review was a critical part of that. The feedback on acting is, if we take an action, was it the right action to take? And if it was the right action, how effective was that action? Right? So if I have an action that is good for mitigating 5 threats, and I discover that, well, really there's about 15 out there that it should be mitigating, I might say that it has a low effectiveness because it's only doing about a third of what it should. And we should really work to improve. So when I want to summarize kind of all of what we talked about in the cyber OODA loop, we can kind of look at it in the context of the data, information, and knowledge model in the center. And so when we think about down at the data level, we have all the sensors, looking at logs and activities and things like that, right, producing those. We have all the analytics and machine learning and scoring engines applied to all those observations. And then up to the information area, we have information sharing services. We have this cyber investigation analysis standard expression, which is really about capturing all the investigation activities of the defender. We have on the other side, STIX, the structured threat information expression for threat intelligence, which shares threat intelligence over a service called TAXI, the Trusted Automated Exchange of Indicator Information. And a good example of that is DHS's Automated Indicator Sharing Service, which if you're not getting threat intelligence from that and you need threat intelligence, I would certainly go out and register for it because it's free, right? And so when we think about the second part of sense making, when we get into the knowledge area, I call that 2B sense making, because if you think about, I'm getting a prediction from here, I want to validate those predictions up here with the cognitive playbooks and knowledge engineering, so I can take my human experience or my enterprise knowledge or my domain knowledge and use that to validate the predictions coming from these different data sets. And then I want to make sure that I can make decisions. I want to understand what effects my decisions are going to have on the adversaries. And then I want to take that action, and then I want to look for evidence of how effective the action was that I just took. Because for every action, if you understand the effect that you're going to have on the adversary, then you can go and look for evidence of whether it was effective or not. So that way you can provide that feedback across the different stages, and particularly into your acting or your response. So that way you can improve your response. And when we think about cyber defense, we think about the cybersecurity framework, just to give you some insight on automation and human sides of it. We think about identity, kind of the first area of the cybersecurity framework. That's almost all automated. It's almost all tools. And scanning, it's just a matter of assembling that data, right? When we think about protection, we invest a lot of money in protection devices. That's almost all automated, right? That's all the stuff, all the firewalls and intrusion detection systems and continuous diagnostics and mitigation and things like that we employ. When we get to detection, it's about half and half. It's about half automated and about half manual, right? That's why we keep applying more and more data science algorithms to more data sets to detect more patterns. We're building more cognitive playbooks to look at the evidence by itself, even without a prediction, to validate what's in there. But when we get to respond and recover, those are increasingly humans doing that activity. Now there's the IACD effort that's really been trying to push security automation and orchestration on, but just remember that a lot of those activities are going to be human driven. So when you're producing results and you're expecting a human to take action on it, make sure that you're providing as much information or aligning it to their type of knowledge, those cybersecurity frameworks, and make sure that you're speaking kind of their language so they can respond faster and find more value in the solutions that you're building. So with that, I'll open it up for questions. So I'll give you an insight. So I've spent the last 8 years focused on knowledge engineering, right? That symbolic AI side. But prior to even looking at that, I'd had close to 20 years of exposure of statistical models, right? So for me, we can apply data science down here at the data level again and again and again, but there's also an opportunity for data scientists to apply algorithms inside the integrated knowledge. So I can pull all this knowledge together, and then I might be sitting there in my AI head saying, it would be really great if I could think about probabilities. What's the best probable action? So logically, I have 3 responses that are logically sound. I might want an algorithm that says, well, give me the probability of which one's the right one for this, and to be able to take it. And then I can get feedback on whether that probability was right. But if we're not building integrated knowledge, we'll never get to apply those algorithms in that next level inside integrated knowledge instead of on a siloed data set. Because when I think about all the data science efforts, they're just building analytic silos. Analytic silos that I, as a human without this, have to put together in my head. So if you look across at the thousands of solutions in cybersecurity and cyber defense producing information, that's a lot of information to make an analyst, a cybersecurity analyst, have to understand all of those different data models and how they're all connected together and how they're all aligned to all that external community knowledge. So for me, focusing on knowledge engineering was trying to help everybody else who is a cyber defender, because they just don't have that capacity. Yes, sir. I haven't. Decision making is really a human process at the moment. And so what we're really focused in on at the moment is building trust. You can imagine that a lot of the predictions coming out of a black box solution doesn't help build trust, right? So we're having to apply some other types of AI in order to, let me take that prediction, run it through this cognitive playbook, build a transparent, explainable explanation or a scientific argument based on what it's seeing. So that way, that result, that prediction that originally came from machine learning has now been validated, and we can explain exactly why, because the evidence is going to tell us why we think that, the claim is going to be what we think, and the evidence is why we think it, and the reasoning is how the evidence supports the claim that we're making, and we can tie all that together in transparent things. And that's just to inform decision-making, even before we get to decision-making where you have to think about and go across and understand, well, what effects can I even have? Is there even any response knowledge going across? Because if I don't have any response knowledge, our AI has nothing to do but pass it over to a human and say, hey, you haven't told me what to do in this situation, right? So we have to help defenders have those kind of matrices to understand and map all their defenses. So if I was looking at something like the cyber effects matrix, and I wanted to go across and understand, as an incident responder, I want to go in and map every single place of those 400 different activities where I actually have a validated incident response plan. If I don't, then I'm flying by the seat of my pants, right? So it's all really about identifying the gaps that we have. What can I see? What can I respond to? What effects can I have on the adversary? What don't I have the ability to have an effect on? Or what can't I see? Because that's going to inform my funding. What am I going to buy next, right? If I have a big gap in my visibility, I might buy a whole bunch of sensors to increase my visibility. After I increase my visibility, I might buy a whole bunch of analytics to make sense of all that new data that I'm looking at, right? And then I might invest in human expertise to build cognitive playbooks to validate all those predictions. So it's really a step-by-step process, but I don't think we've gotten to that point of really focusing on automating the decision as much in cyber defense. Because remember, if you automate an incorrect incident response, you might have just wasted $1 million.
Hello. So I recently got a hold of the report coming out of the Executive Order 13800, which is to strengthen cybersecurity. And in that, says that federal agencies should follow the cyber threat framework. But then in the same document, it has what looks like the MITRE navigator diagram. So I'm a little confused. So first of all, does the OODA cyber threat framework have its own set of techniques that we're supposed to use?
So it does. So if you think about MITRE's tactics and techniques, they don't have any stages of the cyber attack life cycle, right? Because they kind of consider the tactics as being their own stage. With the OODA, they added the stages up at the top, but then all of these are the equivalent of MITRE's tactics, right? So what they did is they drew from community sources. The reason why I don't necessarily like using layer 2 and layer 3, I'll call it, of the OODA cyber threat framework is because it's only accessible in human understandable formats, whereas all the MITRE stuff is available via API, right? So we took the initiative even last year of starting to integrate these models together. But really the MITRE's tactics at the top of their thing are what the OODA calls objectives. MITRE sometimes explains those as objectives or goals of the adversary, and then the techniques are the activities or behaviors that the adversaries are going to do to achieve that objective or goal. And in this case, the activities or techniques are what the OODA calls actions. And then indicators is obviously all your artifacts and who did what. The cool thing about pulling in and integrating these different solutions together is when we get into the cyber effects matrix, when you look down in kind of this area, we have, the ability to explain all the definitions of everything in here because we've encoded that knowledge. We can pull up mitigations, and the mitigations might be resiliency techniques and approaches out of NIST 800-160 Volume 2, right? Because that's a 500-page document. Nobody wants to pull that damn thing open and try to figure out what goes to what. We've aligned it and actually mapped each resiliency technique and approach to what effect they have on the adversary behaviors, so that way you can glance at these and click on it and understand the note and understand what resiliency effects actually aligns to a particular objective of the adversary, so you understand what resiliency effects you can actually do to have that effect, such as prevent or preempt the adversary achieving privileged escalation, right? Or whatever their objective is. But all of this information, it comes from, integrating things like the OODA cyber threat framework, NIST 800-160, right? Because we also want to pull in definitions of what all these different effects are. And if you're having an effect on an adversary, that effect, in turn, is going to do something to your risk, the risk posed by that threat, right? In most cases, it's going to lower your risk or reduce the impact of that risk. They're resiliency techniques, so they're less likely to reduce the occurrence of the risk, but they're designed to reduce the impact. So, but understanding what effects I can have and what impact those will have on the adversary, and in turn what impact that will have on my risk, is stuff that defenders have to understand. Any more questions? All right. Thank you.